We're going to continue on, and so the problem that we established was that that we can approximate. So we'll say we can approximate the sampling distribution of p hat with the normal distribution. Okay, and the normal distribution have a mean mu equal to p and standard deviation sigma equal to p times 1 minus p over n. Okay, this this is known as so both of these statements together is known as the central limit theorem. Okay, well, to be honest, the central limit theorem is it's a little bit more formal and a little bit more complicated, but from a practical standpoint, this is basically what the central limit theorem says. Okay, the central limit theorem says we can approximate the sampling distribution of p hat with the normal distribution, and that normal distribution will have a mean equal to p and a standard deviation equal to the square root of p times 1 minus p over n. That's the central limit theorem. There are some conditions, however, that must be met in order for the central limit theorem to work, okay? So for the central limit theorem to be true, okay, we have a few conditions that must be met. Okay, we have a few conditions. All right, and so I'm just going to call the conditions the same thing that the book calls them. Different textbooks say name these things differently, but they essentially say the same thing. Okay, so number one is the random and independent condition. And this basically says that the sample that we're dealing with, the samples have to be drawn randomly from the population. So we're assuming that the samples have been drawn randomly, okay? And that members in the sample are independent of each other, okay? And then, the individuals within the sample okay? So if somewhere in the problem it says the sample is drawn randomly, you can assume this condition is met. Okay, so if the problem says random sample, okay, this condition is probably met. But if you have something like you sent out surveys and you got responses, okay, like you sent out surveys to 1,000 people and 300 of them responded, and then you're going to say, you know, out of the 300 who responded, 80% had favorable ratings and 20% had unfavorable ratings or something like that. That is not a random sample, okay? Because you have non-response bias, right? So the people who respond to the survey may not necessarily be representative of the general population. Right. So it has to, so our samples have to be random. Okay. Large sample condition, okay? The sample must be big enough. Sample must be, quote, large enough. All right, and what exactly is large enough? Okay. Either you need at least 10 successes and must observe at least 10 successes and 10 failures. Okay, so, so if you take a sample of 30 people and only 5 of them said yes to the question, you know, let's say you took a sample of 30 people and only 5 wore glasses or something like that, your sample is not big enough to do inference, okay? You have to have at least 10 yeses and at least 10 nos, okay? So you must have at least a sample size of 20, okay? If you don't have a sample size of 20, you definitely won't have at least 10 of each, okay? And probably you want a bigger sample than that. And if we're not dealing with counts n times p has to be bigger than 10, and n times 1 minus p has to be bigger than or equal to 10. So if you don't have the counts, you can multiply the sample size times the proportion to get kind of an expected number, right? So there's 2 ways to check for 10 successes and 10 failures. So that's to make sure your sample is big enough. Okay, and then lastly, you don't want your sample too big. You also need to have a big population. So the population must be at least 10 times bigger than the sample. Okay, if samples are drawn without replacement. Okay, if you're drawing with replacement, then your population is big enough. Okay, you just don't want to. If you're drawing without replacement, you don't want to. You want to make sure your population is at least 10 times bigger than the sample. Okay, because you run into problems if you don't. So, for example, if you have a deck of cards, okay, when you first draw a card, there's going to be, the deck will have 26 red cards and 26 black cards, right? So you have a 50% chance of drawing, let's say, a red card. Okay, let's say the first card you draw is red. Then what remains in the deck is actually now 25 red cards and 26 black cards. Okay, and so your probability of drawing red is no longer exactly 50%. It's slightly different. Okay. What we say is that if you're drawing less than 10%, okay, if your population is 10 times bigger than your sample, the amount of change that happens is small enough for us to ignore it. Okay, but you know, let's say you drew out 6 cards, and they all happen to be red just from chance. Okay, then what remains in the deck is now significantly different. There's now only 20 red cards and there's 26 black cards. And so because of that, the probability of drawing a red or black card is now significantly different than what you originally started with. Okay, so that's why we want to make sure the population is big. Okay. All right. So I think, in today's lab, if you went to lab section, or if you go to lab section, you're going to be creating a sampling distribution. You're going to have a population that consists of ones and zeros, and you're going to draw random samples from that population. And you're going to repeatedly draw samples, and every time you draw samples, you're going to calculate a new p-hat. And you're going to keep track of all of those different p-hats, and you're going to talk about what your resulting sampling distribution looks like. Okay. All right, is this okay? The central limit theorem? Okay, so if we know what the sampling distribution looks like, we can start to talk about doing inference. Okay, so now that we know what a sampling distribution looks like, all right, so what's going to happen here is we're going to say, this time we're just going to observe a sample. Okay, and we do not know what the population looks like. So based on our sample, what can we say about the population? Okay. So for example, let's say I have a bucket, okay? And in this bucket, we're going to have, I'm keep talking about candy pieces, all right? Let's say we've got Skittles here, all right? Big bucket of Skittles, all right? And you're going to take a scoop out of the Skittles, okay? Scoop of candy, all right? So we take that out, okay? And you count all of the different pieces of Skittles candies here, okay? Okay, so in your scoop, in your sample, it's going to be a random sample of Skittles candies. Let's say you have 80 pieces of candy. Okay, and let's say 13 are red. Okay, so 13 pieces are red. Okay, so what is that sample proportion? 13 divided by 80 is, what is that? That's 0.1625. Okay, so your p-hat is 13 over 80, 0.1625 of your sample is red. Okay, what can we say about the entire bucket of candies? Does that mean the bucket is 16.25% red? What can we say about the proportion that's red in the bucket? Based on my sample, this is the question that I'm asking. Based on my sample, what can I say about the proportion of candies in the bucket that are red? Can I say anything? Maybe, maybe not. What do you guys think? I can't say anything? Huh? I should do more what? No, this is like someone, you said, can I take a scoop of candies out of your bucket? And they said, okay, but you only get to do it once, right? So this is what you have. You get one scoop of candy. You got 80 pieces of candy in there. 13 of them are red. What can we say about the bucket now? Okay, you can't, huh?
At least 0.1625 red already.
Not necessarily at least, but what we can say is that, well, I don't know exactly how much is red in the bucket, but I'm thinking the amount that's red in the bucket is close to 16%. Maybe it's more than 16%, or 0.1625, maybe it's a little bit less than 0.1625, but I should expect that in the bucket about 0.1625 are red, okay? I would be surprised if the bucket turned out to be 90% red, okay? That would be pretty surprising to me, okay? I would also be really surprised if the bucket was only 1% red, right? It would be reasonable, I mean, it's possible that the bucket's only 1% red and I just happen to get a sample that's 16% red, but that would be, really surprising. I would expect that the bucket's something around 16%, maybe between 10 and 25% red, I don't know. But I would expect something around 16% to be red, something around there, okay? All right, so let's, so put this thought on hold here, and I'll do a little illustration here that I hope, I don't know, maybe it will help us understand. Maybe not, who knows? Okay, all right, so let's say somebody, so here's a picture. This is a picture of, that's a picture of a dog, all right, on a football field. And we'll say the dog is at the 30-yard line on the football field, okay? All right, maybe it's on Snapchat, so because it says, and it says invisible owner, where? All right, so basically we're going to say the dog has been spotted at the 30-yard line on the football field. Okay, but somehow we're also going to say the dog is actually on a walk with his invisible owner. Okay, and the dog actually is on an invisible leash. An invisible elastic leash. And so, you know, we have no idea where the owner is. Okay, so we don't know where the owner is. But we do know a few things about the behavior of the dog. Okay. Okay, and what we do know is that, you know, the dog doesn't like to get choked by the leash, so that 68% of the time the dog stays within 1 yard of the owner. Okay, and 95% of the time stays within 2 yards of the owner. And then almost all the time, 99.7% of the time, dog stays 3 yards of the owner. Okay? Now, because it's elastic, the dog could go more than 3 yards away from the owner, but that doesn't happen very often. It only happens 0.3% of the time. Okay? So only 0.3% of the time will the dog be more than 3 yards of the owner. Okay? But sometimes happens, right? Sometimes it happens. Okay, so if I say we see the dog at the 30-yard line, can we say anything about the location of the owner? That the owner's right next to the dog? What can we say about the location of the owner? Could the owner technically be anywhere on the field?
Yeah.
Technically, yes, because it is an elastic leash, right? So the owner could technically be at like the 25-yard line. But that would be surprising if we find out that the owner was at the 25-yard line. We would be surprised because that means this picture happened to be taken at one of those very, very rare moments where the dog was 5 yards away from the owner, which doesn't happen very often, okay? So based on the behaviors of the dog, we can say something like, I am 95% confident that the owner is between 28 and 32 yard lines. All right. Does that make sense? Okay. So I can't say that for sure the owner is between 28 and 32. But I can say because 95% of the time the dog stays within 2 yards of the owner, if I see the dog at the 30, I can be 95% confident that the owner is between 28 and 32. Okay? Now it could be that the owner's out at 33 or even farther away, but that would be rather surprising to us because then that means this picture was taken at one of those relatively rare occasions where the dog went more than 2 yards away from the owner. Okay? So the idea here is that the dog is similar to our p hat. We can observe where p hat is, okay? We don't know where the owner is. We don't know where p, the population proportion, is, okay? And all of this stuff, this is basically stating that the sampling distribution of p hat, the behavior of the dog, or the behavior of p hat, sampling distribution of p hat, follows the normal distribution. Okay, and instead of 1 yard, we have one, what we call a standard error here. Okay, so flipping back to this thing, if I see that my p hat is at 0.1625, what can I say about the proportion in the bucket, about the population proportion p? So let me just kind of copy. So from earlier we have this, okay? And so what I'm going to say is that, okay, because we know p hat follows a normal distribution, or because we know, the sampling distribution of p hat follows the normal distribution, okay, we can say that our value of 0.1625 is most likely, I'm going to just put in the vague term, somewhat close to the population proportion p. Okay? And in fact, we can be more specific, so more specifically, we can say, I am 95% confident that P is within, we're going to say within 1.96 standard deviations of our p hat 0.1625. Okay? What are the standard deviations of our sampling distribution? This was the square root of p times 1 minus p divided by n. Do we feel okay with what we're saying here? Okay. There is one caveat, and that is this standard deviation uses p, which is unknown to us, right? Okay, so I'm going to write the standard deviation of our sampling distribution This is also called our standard error. And that is equal to the square root of p times 1 minus p divided by n. Okay? If p is unknown, okay, which often the case, okay, we estimate the standard error by substituting p with p hat. Okay, so we're going to use our sample proportion as a stand-in for the population proportion. So our standard error becomes p hat times 1 minus p hat divided by n. Okay, so when we do confidence intervals, we don't know what p is, so we're going to plug in the value p hat as a substitute for p. So I'm going to put all of this together and say, you know, so I can make a 95% confidence interval. And say, I am 95% confident that P, the population proportion, is between P hat minus 1.96 times the standard error, P hat times 1 minus P hat over n, and P hat plus 1.96 times the standard error, P hat times 1 minus P hat over n. Okay. Don't let the formulas and all the letters confuse you. All we're doing is we're just saying I'm 95% confident that the owner is between 28 and 32. How did I get 28 and 32? I did, well, if I see the dog at 30, 30 minus 2 is 28, 30 plus 2 is 32. Okay, yes?
Why did you use 1.96 instead of 2?
Yeah, why did I use 1.96 instead of 2? And that's because if you look at the normal distribution and we wanted to get the middle 95%, we can say approximately the middle 95% is between 2 and negative 2. But if we want to be more precise, the numbers we should be using are 1.96 and negative 1.96. Okay? If you look at your normal table and you want the middle 95%, okay? The middle 95%, if I go to 1.96, I get 0.975, which means I have 2.5% in the upper tail. And if I go to negative 1.96, I also have 0.025. Okay? If I go to 2, I have just a little bit less than that. I have 0.0228. So if I go out to 2 and negative 2, I get just a little bit more than the middle 95%. I get something like 95.5%. And that's why we use 1.96. But if you use 2, you're going to get something pretty close to it. But that's why we're using 1.96. Yeah, question?
So then should we use 28.4 to 29 point, or like 31 point?
Oh, yeah. Oh, so the with the dog?
Yeah.
Yeah, I guess technically we should say, yeah, 28.04 and 31.96 yard lines. But yeah, just, I mean, for that illustration, we're going to say something like that, okay? But yeah. Okay, so let's try an example here. All right, or let's do our Skittles candy thing, okay? So we have is that p hat is 0.1625, okay? So my standard error, the estimated standard error, would be technically p hat times 1 minus p hat divided by n. So I have the square root of 0.1625 times 1 minus 0.1625 divided by 80. What is this? Okay. Square root, okay, so we're going to do 0.1625 times 1 minus 0.1625 divided by 80. Oh, syntax error. All right. Oh, of course. Close off your parentheses. Very important. 0.0412. Okay, that's my standard standard error. Okay, and then so my lower bound will be p hat minus 1.96 times the standard error. So I'm going to have 0.1625 minus 1.96 times 0.0412. And on the upper bound, I'll have 0.1625 plus 1.96 times 0.0412. Okay, so I'm going to multiply this times 1.96. Okay, and I have 0.0808, so I'm going to have 0.1625 minus 0.0808. All right, so let's do this. And I get 0.0817. Oh, what happened? What happened? Okay, and then on the other hand, I'm going to have plus 0.0808. That's what's that? 0.2433. Okay, and so putting this all together, we'll say, you know, in my random sample, "13 out of 80 pieces were red." Okay, or 0.1625 are red. So based on my sample, okay, I am 95% confident that the proportion of candies that are red in the population is between 0.0817 and what was my other number? 0.2433. Okay. So based on what we see in our sample, we are 95% confident that the proportion of red candies is between basically, you know, around 8% and 24% red. Is that okay? Could the proportion that's red actually be outside of this range? Yes. Okay. So could the actual proportion of red candies be, you know, 25%? Yes, that is possible. Okay. However, we would be surprised if this were the case. You know, a bit surprised. If that were the case, it means that our random sample had to be one of those rare times where we happen to get just far too few red candies than what was actually in the population, okay? It means that our random sample happened to produce a sample with an unusually low red candy count. Okay, but it happens because it's random, right? Because of random chance, you might get a sample that is unusually too much red or unusually too low red or something like that. Okay. All right, so putting everything together, our formula, our confidence interval equation or formula is p hat, and then because you have a upper bound and lower bound, we're going to combine just the plus and the minus together. So one side is p hat minus this, and the other side is p hat plus this. We're going to have z star times p hat times 1 minus p hat over n, okay? Z star is called our critical value. And, you know, if the confidence level is 95%, then Z star is 1.96. Okay? But sometimes you want to make different confidence levels. If you're okay with lower confidence, you'll use a smaller Z star, 1.645. Or if you want 80%, you would use Z star equal to 1.28. If on the other hand you want extra confidence, 99%, you would use Z equal to 2.578. I'm sorry, 2.58. It's 2.576, or we'll just round up to 2.58, and that's fine. You could calculate this value by yourself. It's so that, you know, if you want the middle 95% here, you'll have 95 here, and 0.025 here, and 0.025 over here, okay? And, you know, likewise, you'd draw similar pictures for the other confidence levels, and you get similar things. I would say these are probably the most common values, so these are values you should, I don't know, but you know, they'll also show up on kind of formula sheets and things like that. All right, have a good weekend. We'll see you guys on Monday.